One application of first order linear differential equations for modeling is LR and RC circuits. Okay, L stands for inductor, R is resistor, and C is capacitor. Okay, so we don't look at LRC circuits, which would require second order differential equation to model. So we'll focus on either LR or RC because they're first order. Okay. Now the voltage, the potential difference across an inductor, V sub L, is equal to L di dt. Notice this is first order in current. But if we were to use charge, well, current is actually the rate of change of charge. Okay. So we're focused here on first order problems. We're also not going to look at an LC circuit, for example, because then we would have to go down to second order. But if we just focus on LR, we could use di dt and I and just get a first order differential equation in I. Okay? So L is a constant called the inductance. VL is the potential difference across an inductor. I is the current through the inductor. Q is charge, even though it doesn't show up here because of what I was saying. Okay, we're going to focus on first order. V sub R is the voltage across a resistor. Ohm's law tells us that the voltage across a resistor is the resistance times the current. Okay. I also just make it explicit here that I is dq dt, even though we won't be using that here. So, this just defines what I just said. V sub C, the voltage across a capacitor, is equal to the charge over C. Okay? And so when we're looking at an LR circuit, we have Kirchhoff's second law, which tells us that the sum of voltages across a loop in a circuit is 0. So if we have some source, okay, this source could be a battery or some voltage generator. And, it could have square waves, triangular waves, sinusoidal waves, just constant, which is just a battery, and on. But we just leave it general as E of t being the potential difference across this source. Then when you use Kirchhoff's second law, you get, plus E minus the voltage across the resistance minus the voltage across the inductor is equal to 0. And so you end up with this differential equation. Once you plug in for VL, you plug in L di dt, and for VR, you use Ri, okay? And we get a first order differential equation in I. RC circuits, similarly, except this time we're going to use actually dq dt because we'll get a first order differential equation in Q. Okay? So again, we're focused on, we're not going to reduce this to d squared q dt squared or, dq dt because we just want to solve for I. We want to stick to first order. And so if we stick to first order, both of these, then we're going to use this form here, okay, for the potential differences. So let's look at an example of a LR circuit. We have a 12-volt battery connected to a series circuit. So we just focused here on series circuits. Series are these simple circuits here without going into physics, but they're all connected together. There's no splitting of the currents. So it's a series circuit. E of t is 12 volts. Okay, so it's a series circuit, 12-volt battery. The inductance, which is measured in henries, you have 1/2 Henry, so 0.5 Henry. And the resistance is measured in ohms, and you have 10 ohms. The resistor is 10 ohms. Determine the current I if the initial current is 0. So just writing all that out, taking the word problem and writing out the parameters, we get these values here. And here's our differential equation. For L, we plug in 1/2 Henry, and I didn't write the units there to just kind of avoid a lot of symbols. R is 10 ohms. And 12 here is the battery, okay, 12 volts. And so we have this differential equation. It's linear, of course, and we could use the linear method to solve it. We get our integrating factor, here it is. And so we get this relation here with the integrating factor times the right-hand side. We integrating a derivative is straightforward, and then we integrate the right-hand side. We get this. And so here's our general form for the current. How do you fix C? You fix C by the initial conditions, which is the current is 0 at t equals 0. Two pieces of information. One is given in the word problem, the other by plugging in t equals 0 into our general form. We solve C for C, and we get negative 6/5. And so now we have our current. And down here, I just basically write the general solution to those two equations above there. Okay, if you use the linear method, you get this general solution. So notice that E of t could be very complicated. It's not just a 12-volt battery connected there. For the RC circuit, you would get this general solution there. But I would encourage you not to use the formulas and actually just solve the differential equation. It's probably easier once you have a particular form for E of t to just solve directly rather than relying on this clunky general solution. And something to note here about this general solution, I write const here, so I don't write C. Okay, that's the only reason why I wrote const. I noticed when writing C here for the constant that some may confuse it with capacitance, even though there is no capacitor in this circuit. Of course, it's a RL circuit, no capacitor. But just to, out of abundance of caution, to avoid that C being confused with capacitance rather than just a constant, I write const for these general solutions.